Hello, my name is Véronique Michaud. I'm from EPFL in Switzerland, and I'm very glad to be here today, even if it's virtually, to present you the work that we've been doing at EPFL with my colleagues, Amael Coad, Robin Triguera, Nathan Hostetler, and Cecilia Scazzoli on an idea of future composites to be more sustainable with tough, healable, and maybe recyclable composites. So to start, I will just go by showing you a hockey player that is done a lot in Switzerland. And you see the poor hockey player broke his stick. And this, of course, is done of composites. We have a lot of possibilities, as you are all aware, with composites for lightweight design, with fibers and resin. But it can lead to micro cracks. And these micro cracks, when they coalesce, can lead to failure of the part. And this is not only true for hockey sticks, but it's also true in many other applications, whether it's for boat building or, for example, for sailing, or it's for automotive or energy applications. All this creating for cost, additional cost of composite repair and issues about the sustainability. So what are the current strategies when you have a composite failure that you would try to avoid? Well, of course, the strategy is to inspect and do or monitor, for example, for a windmill blade every so often by sending people there. And then when you see that there has been damage using, for example, ultrasonic techniques, you can repair, which takes a lot of time, or you can actually throw away if it's a pair of skis and it's beyond repair. Of course, this all creates long downtimes, necessitates manual intervention, and is very costly, and needs also very skilled labor. And what can be done then is to evaluate the cost. And for example, only in windmills, it was evaluated to $13 billion in 2020. So it's an important point. And the needs of the market would be to be able to repair and process on site, which starts to be done in some cases, but at a limited cost with no loss in properties and with a manufacturing that is compatible with the manufacturing that we have. Now, what are the additional strategies that we can use to mitigate damage? Of course, there is a lot of research on limiting damage growth by improving the intrinsic resistance to crack propagation, for example, with toughening matrices, or different design variables that can be changed to improve the resistance of the structure. But another possibility is to accept that you will have damage events and propose a method would ideally localize the damage, locally close cracks if needed, and heal the material. All this without compromising, of course, the structural integrity of the composite. So it's a little bit like a skin wound that you would have. And by adding sutures, for example, you can actually help the crack to be closed if it's too big, or if it's not big, it would simply heal by itself. Of course, we're not talking about skin here. We're talking about structural fiber reinforced composite structures, in particular those made by liquid composite molding, for example, which requires to have a resin that is typically a thermoset epoxy, could also be a thermoplastic, then fabric, and by infusion, for example, or RTM or other processes, you mix the fibers and the matrix to create the composite. And as an example of delamination or matrix microcracking after a low energy impact event, you see here in this figure, that's an X-ray pictures of after a 5 joule impact of a composite, that you have a lot of microcracks that are present inside the composite. They may not be so severe, but if you do not do anything about these, the integrity of the structure might be damaged. So our initial approach to heal cracks was to propose to use a composite that would be load-bearing with a high volume fraction of fibers, but add a healing agent inside the composite so that if there is a crack, for example, with a matrix that has fiber reinforcement bundles, but also this matrix made of little phase-separated thermoset and thermoplastic mixture, that if the crack takes place after moderate thermal trigger, you will fill the crack with the thermoplastic phase that will flow into the crack and heal the crack through this phase. Of course, this requires heat We did a lot of work previously on healing without heat, but then the material is normally too soft at room temperature, so it becomes very difficult to work with this material. So our choice was to go for this assisted healing using thermal trigger. There are model systems that exist in the literature, and we got inspired from a paper that was published in about 10 years ago by Luo et al. On intrinsic self-healing with phase-separated matrices using a PCL in an epoxy, a traditional JEBA resin. He showed that by heating at 190 degrees for 8 minutes, you got complete healing, and that, in fact, it depended a lot on the microstructure, which itself is a function of the volume fraction of PCL, or the mass fraction of PCL in the blend. And depending on the mass fraction of the PCL, you get polymerization-induced phase separation with different morphology. What he showed also is that in his case, around 15 weight percent PCL was good for the healing, thanks to the PCL expansion. And what he shows is that because of this heat expansion of the PCL after melting, you get the possibility of the PCL to bleed. And this brick and mortar morphology, as he called it, was the best one to obtain this bleeding and healing of the PCL phase. So we started exploring these blends and worked on model systems, which with the epoxy and PCL, mixing, curing at 3 hours at 180 degrees. And then we got phase separation. In our case, we found that about 25% of PCL was the good one that we needed. And then we see, of course, that the storage modulus at 25 degree and 150 degree, which is the healing temperature that we will use, is decaying with the presence of PCL in the matrix. However, it remains in a range about above 1 gigapascal, which is acceptable. We see also that we have this microstructure that was proposed and observed already by Luo, and that in the fracture surface we have all kinds of mechanisms taking place depending very much on the morphology of the blend. So we saw that if you increase the volume fraction of PCL, you get very good toughness properties for low volume fraction of PCL, but as you add PCL, you lose a bit in toughness of the material. But as you add PCL, of course, you increase a lot in terms of healing efficiency, which was a toughness recovery in TDCB configuration in our case. So there is a region where you would have something that leads to a decent healing, yet you don't lose too much in terms of the toughness of the material. And we found that it works, and you get a good healing efficiency after several healing cycles. And that depending on the blend, of course, you check that actually it's really a phase-separated blend where the PCL is still obvious in the DSC traces, as well as the epoxy glass transition. Note that the epoxy glass transition is high enough so that thanks to this connected epoxy morphology, when you heat up the material to 150 degree, you don't lose all mechanical strength because you still have this network of epoxy to keep it. So then we considered if we could use it as a matrix. So we put it into a composite with fibers. The idea again being that if you have a crack, then upon a small heating at 150 degrees for half an hour, for example, you have the PCL bleeding, and then you will end up closing the crack. So we saw that it actually works. We looked at the morphology, and of course, the presence of fibers will affect a bit the phase separation. With the big resin pockets having the normal phase-separated morphology, smaller resin pockets having a different morphology, yet we still see that it works. We also checked that there was no loss in modulus compared to pure epoxy reference composites, and that we had a stiffness recovery over several damage and heal cycles. The energy release rate, however, decreased quite a lot as compared to the reference epoxy composite due to the loss of toughness of the matrix. And we had a moderate toughness recovery due to incomplete crack fill. So we had something that worked, but of course, normally you don't have a DCB test happening in real life. So damage could be, for example, under the form of an impact, creating some micro cracks. And we looked to see if we could really heal the micro cracks. So we did this experiment of an impact where we expected the healing to take place, and we checked already visually with glass epoxy PCL composites that after healing, the damage impact started to disappear, and if the energy of impact was not too high, after moderate healing, we could see already that it disappears completely. We checked this with C-scans to see that we have this effect depending on the energy with a low enough energy, but 8.5 joules is already quite decent for a composite. Remember the picture I showed with 5 joules before, leading to a lot of micro cracks. With this, after healing, we got almost all the surface filled up. We did compression after impact test to show that the compression after impact of the composite with the PCL is actually lower than that of the plain reference composite, of course, as the material is a little bit reduced in properties. But after healing, we have this blue curve that shows that, in fact, the healed material after impact, of course, this one you don't heal because it's a normal epoxy. This one, if you do an impact at this energy and then you heal up, you will almost recover the properties of the pristine composite after impact. So it was encouraging. Of course, this is not yet perfect, but we could see that it works. And that, of course, the healing efficiency decreases a lot with impact energy because we cannot recover fibers that are broken, but we can recover microcracks fairly well. So healing was also possible over multiple cycles, and at high energy, as mentioned, it didn't work. So to increase the toughness, because this is really the Achilles heel of that PCL material, we considered the use of nanofiber mats. And this was a collaboration we had with colleagues from Ghent University, where they make electrospun PCL nanofibers, which we integrated into the composite with one PCL nanofiber between glass fiber fabrics. Then we impregnated with an epoxy resin, we cured, and we looked at the properties. We used different ways of curing the material, and then we did some DCB testing to look at the toughness of the material. We had a plate that was an epoxy plate that was our reference material with the G1C around 1 kilojoule, a bit over a kilojoule per meter square. Then we did a plate which was cured at room temperature only, one that was cured at 60 degrees, so above the melting point of the PCL, and one that was cured at 80 degrees, so way above the melting point of PCL. What was interesting is that in all the 3 cases, the toughness of the material was quite improved. Whether we actually preserved the nanofiber mat structure below, so it was not molten and it remained, or actually even a bit better above the nanofiber mat melting. So we had melting and phase separation, which we could actually see in this SEM picture. You see that this is the matrix. You see a lot of different things happening. But if we look a bit more carefully, in some regions, you see that you have an epoxy-rich region with a bit of PCL particles. In other regions, you have a phase separated domain. And then in the final region, you have epoxy particles clearly visible in the matrix, showing that we have this phase separated morphology we were looking after. So we get a good toughness improvement. Do we get healing? Well, we did the same experiments as before. We closed the crack. We let it for 30 minutes at 150 degrees. And unfortunately, no healing was observed at all. And we understood why and published this actually. It's attributed to the shrinkage of the stretch polymer, and most importantly, the PCL that we use at a high molecular weight in this case, with a very high viscosity, a very thin microstructure. So it was very difficult for it to flow within the narrow channels. So our conclusion at that time, it was a few years ago, was that if we look at making a tough and healable composite, it is a challenge. We can get this being the epoxy glass woven fabric baseline. With the PCL nanofibers, we get high toughness, but zero healing. This is the healing here. With epoxy PCL microparticles, we tried. We also got a good, decent toughness, but no healing. With the blends, we had a decent healing, but no toughness. And we also tried with films interleaved between the epoxy, full PCL films. We got, of course, very good healing, but we had no fracture toughness at all due to the presence of those PCL films. So to get to a place where we get decent healing and decent toughness, we tried different things. One was to blend, use the same blend or similar blends, but with shape memory alloy wires, and only with 1% of these shape memory alloy wires that are stitched inside on the fabric and then impregnated as usual, we got decent results. We can show it here. This is a picture where you see the fibers being broken after we really opened the crack. But if we do DCB with a forced displacement, we see that in the zone where there was no SMA wires, we get a normal behavior with the normal behavior that we had. But then at this zone where we started to have the SMA wires stitched, then we had a big threefold increase, actually, of the fracture toughness due to the presence of the stitched SMA wires. This has been well known, actually. Adding stitching increases a lot, and we elucidated the various mechanisms that take place. However, we see also that after damage, we have the crack that is open, but after healing, the fact that we heat up will help also the shape memory alloy wires to shrink and to close the crack. So this really improves the crack closure and the healing. We also check this for small cracks. So after impact on those shape memory alloy stitched plates, we had a very good healing efficiency. And we see that compared to the ones without the SMA stitches, we also had a much better healing efficiency at moderate impact energy. However, this is not really a suitable solution because it can be used in specific areas, but it increases a lot the weight and the cost. So what to do next? Next, we worked a lot. This was after my colleague Amael Cohen had just finished his PhD. And we thought of an improved matrix system, which is now in blue here somewhere. And I cannot really tell you what we put in there because we filed a patent a few years ago, which is still pending. But we managed to improve the fracture toughness, yet preserve a good healing efficiency. So we went on with the system. We saw that it still retains a very good impact on healing. So this is a reference epoxy as usual, and then the reference healed. We see a bit of resin relaxation, but the damage is still present. And in the healable composite, we have a full healing of damage. And then again, we checked it with compression after impact. And we saw that the healing efficiency of the healable system was very good, again, at low energy, quite good at a moderate impact energy, and quite decent at high impact energy. And we see also that we have increased the resistance and the healability of our material compared to our initial blends, because we increased also the toughness, which makes the material less sensitive to damage after impact initially. So this was very interesting. And then if you have the pure resin only after heating 150 degrees, the reference system, we see that we have a bit of healing due to resin relaxation, but it is a very not reproducible with a very large variation in the properties. Another thing that we looked at was the aging performance of this new matrix material. And as compared to the reference system, by putting it at 80 degrees in a high relative humidity for several days, we saw that there is a water absorption that is a bit higher than what we would have for reference epoxy, and a bit of decay in short beam strength after this exposure, but actually not so bad as compared to epoxy system, so it was still acceptable. Then we looked at the fatigue performance of the systems, because we suspected that if our material can heal small cracks, it should be able to heal fatigue cracks. So we did a 3-point bending fatigue test, normalized to 50 volume fraction fiber, presented here, where you have the SN curve. This is the material, the virgin material. So our healable material is a little bit lower in property as expected as the initial reference material. However, we see that with the number of cycles increasing, there is a crossover, and the healable material becomes quite a bit better at high number of cycles than the reference material. Now, what is interesting is what's happening if we do a healing treatment. So for this, we had to find when to do the healing treatment, and we developed a model for the probability of survival, which helped us to find the probability of survival as a function of number of cycles for the healable and the reference composite. And we see, for example, if I put myself here at 248 megapascal, and I have, for example, at this number of cycle, I have about 40% chance of survival. And then as I increase the number of cycles, the chance of survival decreases. So we decided to put ourselves at 90% chance of survival when we do the healing. So which means that we take the material, we do the number of cycles that we need, then we stop, and we put it in the oven for half an hour at 150 degrees, and then we test again. So what we found in that case is that if we look at the bottom, which is the reference material, we cycle it up to 90% survival. Then we put it in the oven, we put it back, we cycle again, and it started to fail after twice the number of cycles that we had done. With the healable material, we put it in, we start at 90% survival rate, we put it in the oven, we put it back, and then it went on, put it in the oven and back up to 10 times without ever breaking the material. So our conclusion was that, of course, we can extend the fatigue life indefinitely, which is maybe to be checked, but at least it's a very promising result. So we went on to do larger scale demonstrators. We made a typical aerospace part with the glass biaxial fabrics. We were very happy to be in front of this, beautiful. And then you see that the video here is mounted on a support. We have a 1.5 kilogram ball that is impacting, and we have the impact that we can see here. We use a simple heat gun for 1 minute in this case, and the impact actually disappears under your eyes. So it's actually quite impressive. Looks like magic almost. And we check, of course, that we recover the initial mechanical properties, and also there is no real change in on the surface, for example, quality of the part and so on. So with this, we went on to create a company after we had filed this patent and so on, which is called Compare, making semi-products for composite manufacturers, which are pre-pregs in this case. So we moved from infusion to pre-pregs with a 400 times faster repair than, of course, having to send a guy, having to cut and do all the repair that would normally be done. Good regeneration, we can do a lot of healing cycles, and we have also an increased crack resistance. So compared to a decent usual resin that people would use. We also, I forgot to mention this, have a potential for improved recycling, and we currently have a project running on finding a recycling route where we can actually recuperate the fibers much better than with a traditional epoxy, and that is also a benefit of this material. Now this is, now got the label from Solar Impulse Efficient Solution. We have different materials from glass and carbon, different types of fibers. And ideally, what we plan to do is really to have a circular vision, providing full circularity to the composites industry. So if you take a composite and you have damage only to the matrix through microcracks, you can actually heal, and then you can continue to use and rotate the material by regular maintenance, and the maintenance being only to heat up at 150 degrees for a few minutes, which could be even done locally by a drone, for example, if you consider a windmill. Then, if you have a damage to the fibers, of course, we cannot heal this damage. And then, in that case, you need to go to the recycling route, and then maybe production and reuse, or to a normal repair route, which is also possible if the damage to the fibers is only very localized and very minimal. So this really goes in the way of hopefully improving the vision that we have of the composite industry by proposing alternative routes to simply discarding, landfilling, or having to repair even small impacts. With this, I conclude saying that composite matrices I've been showing you based on thermoset thermoplastics blends have a good potential for heat-assisted repair. We showed that the integration of shape memory alloy stitches increases the composite toughness and the ability to cause cracks and the ability to repair it, but then we add, of course, weight and cost, which might not be very practical. So we propose a novel matrix material which retains the toughness and ability to repair, and a very good potential for improved recycling as well. I'd like to thank the Swiss National Science Foundation, which funded most of the many theses that we had on the self-healing composite since many years now. Also, InnoGrant, VentureKick, InnoBooster Grant, which are all grants that helped us to kickstart our work and go towards implementation in a startup company. InnoSwiss, which is also funding currently some work on improved materials definition, and Switzerland Innovation Tech for Impact Initiative, funding the work that we're currently doing on recyclability of these composites, which I hope to show you soon. So with this, I would like to thank you. I will be available for questions, and I'm sorry that we could not meet for real, but I hope I will get a chance to visit KAUST, and would like again to thank the organizers of this workshop for the possibility to at least virtually meet all together and share some ideas on the future of composites. Thank you.
Thank you very much, Dr. Michaud. So a very interesting talk and about the recyclable composites. We have one question here in the Q&A. You can actually address it live. It's from Abraham Lagaway. The kind of healing discussed here in your presentation is not renewable. It gets exhausted at some point or saturated. Is it possible to detect when the self-healing process is nearly exhausted?
It depends what you mean by exhausted. This healing is renewable. So you can heal many times. So, and it never gets exhausted as long as the damage, there is no damage to the structural fibers. So, of course, if there is fiber damage, then you will start to, of course, lose properties. So indeed, it cannot just be completely independent. You need to have some kind of inspection that goes with the maintenance operation. So one idea, for example, for the windmill would be to have an ultrasonic inspection on the drone or something like that. And then if you see, depending on the type of damage that you see, if there is a small damage, you just go and you heal it. If there is a medium damage, maybe you can heal it, but you will lose a bit in properties. And if there is a major damage, then you know that you will not heal it. What you can do also, we did a lot, is to do ultrasonic inspection before and after the healing. And we correlate actually quite well. Amazingly, I was quite amazed at the beginning. I didn't want to believe this, but the amount of, the pattern that you see in the ultrasonic scan with the compression after impact properties. So by looking at the scan before and after the healing, you can already pretty much say what the mechanical properties of the material will be. So with a bit of, I guess, if you have a specific material and a specific application case where you know that maybe you accept to have 10% reduction in the mechanical properties, but you would not get beyond that, then you know exactly when you need to repair and when you don't. So.
Thank you. Thank you very much for elaborating. Also, yeah, Michael, please.
Yeah, Véronique, very nice work. Can I just ask you to elaborate a bit more about the compression after impact properties, which aerospace and others are really very interested in? Can you tell us a bit more about that?
Yeah, so compression after impact properties, well, we did a lot during the thesis of Amael. What we see is that, in the case of the materials that we had during the thesis, which were not optimized, the compression after impact is lower. So indeed, we were worse than the normal epoxy at the beginning. And then when there is impact, well, the properties of compression after impact decrease with the increasing impact. But then with the healing, we could recuperate some of the properties back. And what we found with our material is that, of course, it was initially not as good as the epoxy, but it decays and then it came back more or less as the beginning, but of course, never better than it was before. So now with the new material, we still have to do more compression after impact, but we are better initially, and we also are a bit less sensitive to damage than the initial microstructure that we had. So we recuperate a bit better, so we can be a bit we're still a bit lower than the normal epoxy. I mean, a good, tough, state-of-the-art epoxy prepreg, but we are recuperating much better. So we crossed the 2 curve. So it's promising.
Good.
I mean, we're not yet in aerospace, so it's a faraway market, but maybe in 10 years, who knows?
Thank you. Thank you, Dr. Michaud. Thank you for a very nice presentation.